Actually, I have one thing to kind of follow up from yesterday's class. Okay, so one more thing to tell you about uncertainty principles. Okay, and that's because yesterday um, we worked out two equations that are related to commutators. Okay, so from yesterday, um, we have the equation about the generalized uncertainty principle. Okay, and so that says that this, if you have any two observables, A and B, that this product of uncertainties is greater than or equal to something related to the commutator between A and B. Okay, so that's one relation, right? And then we had another relation about time derivatives of some operator. Okay, and that relation is that the time derivative of the expectation value of Q, that is equal to I over H bar, and we have the expectation of the commutator between the Hamiltonian and Q. Plus this other weird thing that I don't like to talk about, but it's in the book. Okay, I'm going to cross off this weird thing. All right, so now, both of these things are related to commutators, okay? And so you might wonder, what would happen if you put them together, right? And so suppose you took the first of these relations, the inequality, the generalized uncertainty principle, and you want to express that in terms of A is the Hamiltonian and B is any old operator Q. Right? And so then this will be the Hamiltonian and this is Q. Okay, and so now this looks like we have the commutator between H and any Q on the right side. And over here, it also looks like we have the commutator between H and Q. So what if we put those two things together? Okay, so then we could combine, we could combine and we would say the uncertainty in the Hamiltonian in the energy times the uncertainty in this other thing, whatever this other thing is, that is greater than or equal to what? Okay, so it's 1 over 2I, okay, and then what? Well, we have this, let's use this relationship right here. Okay, so that is to say, instead of the HQ commutator, we'll put in this time derivative. Okay, so we would get H bar over I times the time derivative of the expectation value of Q, right? That whole thing squared. Okay, and so this is, if we multiply out this square, it's H bar squared over 4, then this absolute value, of the time derivative, like this, right? Or if you square it, no, if you take the square root, the uncertainty in energy times the uncertainty in Q is greater than or equal to H bar over 2. times this derivative of Q with respect to time. Okay. This is sort of interesting, but what does it mean? Right? Well, to figure out what it means, let's divide both sides by this derivative inside the absolute values. Okay, and so that gives us that, the uncertainty in energy times, let's get this combination, the uncertainty in Q divided by the derivative of Q with respect to time, absolute value, that has to be greater than or equal to h bar over 2. Okay, so this thing is the uncertainty in energy. Now, maybe we wonder, what is this thing, this ratio? Well, we could start by saying what units does that thing have, right? So what are the units? Okay, well, the units in the numerator, it is, well, Q units, whatever Q units might be. We haven't said what Q is, so, but whatever Q units might be, that's the numerator, okay? In the denominator, it's the time rate of change of Q. And so that is in Q units per second. Okay. So if you take the ratio, the Q units cancel and we get seconds. All right. So whatever this thing is, it has units of time. Okay. It's a time. Okay. So what sort of time is it? Okay. Well, it has to do with the ratio between how well do you know Q and how rapidly is Q changing. Okay. And the analogy that just occurred to me is looking at COVID statistics, right? Because I look at a lot of COVID statistics. Okay, and so suppose we say we're looking at, COVID cases per time. Okay, so you have December, January, February, March, something like that. Okay, and so at any month, if you look day to day, right, there's a lot of scatter, right? It's not constant. There's a lot of scatter, which corresponds to some uncertainty in what is the COVID case rate, right? And then maybe that's gradually changing as a function of time, right? So maybe the plot looks something like this, okay? So now we might ask, when does the COVID case rate get below a certain threshold? Okay, so we could say, maybe we'll reopen Kent State when the COVID case rate gets below a certain threshold like that. Okay, and so, how well do we know when that happens? Okay, it's a little bit tricky because you can't just look at any one moment because there's uncertainty. It's going up and it's going down. Okay, and so how precisely do we know it depends on both the uncertainty in what is the COVID case rate now and how rapidly it's changing. Okay, so if you had no uncertainty, right? If you knew the case rate with no uncertainty, right, and then you just had a plot like that, oh, well, then you would have no uncertainty about when it crosses the threshold, right? You would say, oh, it crosses the threshold at exactly this time, right? Um, Likewise, if the if there's an uncertainty, but the time derivative is really big, okay, so that would be a plot like this. If there's uncertainty, but the time derivative is really big, then, well, it would be a relatively small uncertainty about when it crosses the threshold, right? Because the time derivative is so big, right? So that the range of time when it might be crossing that threshold is kind of small compared to here. It's a big range of time when it might be crossing that threshold, okay? And so the ratio between, the uncertainty in the case rate and the rate of change, that's what gives the uncertainty in the time for crossing. Okay? And a lot of physical processes are like that too. Right? A lot of physical processes have a certain amount of randomness in it. They have a certain amount of scatter. Okay, and maybe the baseline rate is also changing. Right, something about the process is changing, but there's also scatter on top of the systematic change. And so, how precisely do you know a time depends on the ratio of those two things, okay? And so based on that, we would say this thing is an uncertainty in the time. It's the uncertainty in the time when something happens, right? Or another way to put it would be it's the time that's required for the average Q to change by an amount that you notice, okay? So by a noticeable amount. And what's a noticeable amount? Well, that means more than the uncertainty in Q. Okay. If it changes by less than the uncertainty in Q, it's in the noise. You don't even really know that there's a change happening there. But if it changes by more than the uncertainty in Q, then you know there's a change. Okay. So this relationship then is showing a relationship between the uncertainty in the energy and the uncertainty in the time. Okay? And so people sometimes write that as a delta energy times delta time is greater than or equal to h bar over 2. Okay, so here, uncertainty in energy and this is uncertainty in the time. So there's no more Q in this equation, right? So now this is an equation or an inequality that was somehow derived based on an arbitrary operator Q, but it doesn't have a Q in it anymore. That's kind of odd, isn't it? I haven't quite wrapped my mind around that one. I guess what it means is that if there's a really small uncertainty in the energy, then there's a big uncertainty in the time for anything, right? Any time is very broadly defined, no matter what you're looking at. Okay. And if there is zero uncertainty in the energy, all right, if delta E equals 0, that means we're in a stationary state, otherwise known as an energy eigenstate. Oops, energy eigenstate, like one of the special states of the harmonic oscillator, for example. Okay? And these are states where nothing, no expectation values are changing in time, right? That the expectation values are constant. And because the expectation values are constant, you know, nothing happens at any particular time. And if nothing happens at any particular time, that means that the uncertainty in time is infinite, right? You can't point to a particular time and say that's when something happens. So you know, that's a logical relationship, I guess, which doesn't depend on which operator or which observable quantity you're looking at. All right, so this is now an energy time uncertainty principle. Which looks a lot like the momentum position uncertainty principle. Right? We've known, you know, from early on in this course that, we have this relationship of you know, uncertainty in P times uncertainty in X is greater than or equal to H bar over 2. Okay. So if you compare these two relationships, you know, it looks like the energy time and the momentum position relations are kind of analogous to each other, right? Which is what you might expect from special relativity, right? So you guys have studied special relativity, I guess, in your modern physics class, right? Okay, and so you know that in special relativity, you have, say, a 4 vector, which is energy and momentum. And you have another 4 vector, which is time and position. Okay. And so, you know, based on thinking about these 4 vectors, you would say, oh, well, if there's a relationship between momentum and position, it stands to reason there should be a relationship between energy and time. Okay. So that sounds reasonable, and it makes us, you know, feel as if we're doing relativity. Okay. But oddly, we're not doing relativity. You know, the way that we are working with quantum mechanics, you know, time really is different from position. Right? So for example, in the Schrodinger equation, there's a first derivative with respect to time, but there's a second derivative with respect to position. Right? So Schrodinger's equation really does treat time different from position. It is a non-relativistic equation. Right? There is a relativistic version of quantum mechanics. That's for a more advanced course, right? If you continue on studying physics in graduate school, you would eventually get to a relativistic quantum mechanics course, which has a relativistic version something like Schrodinger's equation. But this isn't it. And so it's a little bit surprising that there is something like relativity, which is showing up here in the context of the uncertainty principle. But yeah, just wanted to point that out for you guys. Well, I guess one more thing I could say about this is this comes up a lot, this relationship between energy and time is related to nuclear physics, right? And so in nuclear physics, right, people are often studying particles or nuclei, which are not necessarily stable. Okay, and so you study particles or nuclei that are unstable. And so that means they have some finite lifetime. A lifetime that is a half-life, right, over which, say, half the particles decay into something else. Okay, so that makes a delta T, an uncertainty in the time associated with a particle or a nucleus. Okay. They also have a certain distribution of energies, right? And so, you know, in a nuclear physics paper, you might see a plot like this, where this axis is the, you know, mass, or relativistically speaking, the rest energy of the particle. And this axis is how often it's observed. Okay. And so a plot like this shows you that the mass or rest energy is not perfectly well defined. Okay? That there is also some uncertainty in the energy, like that. Okay? And then the point of the uncertainty principle is that there's a relationship between those two things. Okay, so that delta E times delta T is greater than or equal to h bar over 2. Okay? So if you have a very long-lived particle, so delta T is big, then the energy can be very well defined. So delta E is small. Right? And vice versa. If it's a short-lived particle, so delta T is small, then the distribution of energies is very wide. Right? Delta E is big. Right? So that's a trade-off that shows up in experimental studies of particles or nuclei with finite lifetimes. All right. So that is, I guess, what I wanted to say about the uncertainty principle. And this, you know, comes into, you know, an experimental application of the general theory with commutators and so forth that we were talking about yesterday. Okay, any questions about that sort of stuff? No. Okay, well, in that case, I want to get into now, I guess, the last part of chapter 3. So chapter 3 is talking about this general theoretical approach for quantum mechanics. And so we're doing this before we go on to 3 dimensions. For the last part, we're going to do a new notation for quantum mechanics, which is called Dirac notation, which is a very nice, compact, convenient notation for working in quantum mechanics. And then this will lead us to a matrix approach for quantum mechanics, which is related to the wave function approach, but a little bit different. And so I'll show you how that works. Okay, but to tell you about Dirac notation, I have to tell you what is got to be the worst joke in the history of physics. Okay, and so this is a joke which goes back to 1939. Okay, but we still have it. We can't get away from it. Okay, and it's based on the inner product. So you guys know now about inner products, okay? And so you know that we have the inner product of 2 functions like this, f and g, okay? So Dirac was thinking about this back in 1939, okay? And he said, well, this is a bracket. It looks kind of like a bracket, I guess, something with f and g. Okay, and then he had the clever idea that it would be useful to talk about the front half and the back half separately. Okay, and rather than have this whole thing be one single mathematical object, we could think of this as the combination of the front half and the back half. Okay, and then he said, oh, well, I need a word for the front half and the word for the back half. Okay, and so he said, well, the front half of the bracket, that must be the bra. Okay, and the back half of the bracket, that must be the ket. Okay, and so he started this concept of bras and kets, okay, to refer to the front half and the back half. And this was like a corny 40-year-old joke when I learned it in 1980. And now it's 2021 and I have to tell it. But that's just the circle of life, isn't it, I guess? Okay, so the circle of jokes. So we are going to think about bras and kets now, and let me show you how you could think about them as separate objects, okay, apart from having them together. Okay. So you know that the whole combined object is this FG inner product, which is the integral, maybe I'll put the dx in the front. It's the integral dx of f star of x, g of x. Okay, so that's the whole bracket, the whole inner product. Okay. So if Dirac wants to break this up into the front half and the back half, okay, so the back half, the ket, okay, this is something which we will just write as G, like that, okay? And so G, it has this vertical line, like an absolute value symbol, okay? And then the label, and then this right side angle bracket, okay? This means won't say equals, but it means g of x. Okay, so it is a wave function. Okay, now what about the front half, the bra? Okay, well, we write it as f like this. Okay, so it has an angle bracket and then the label and then a vertical line like an absolute value sign. Okay, and we don't worry about the fact that there's a vertical line here and there's also a vertical line there. Don't go there. Okay, so that's just the way we write things. Okay, and it means everything else. Okay, so it means the integral dx of f star of x, fill in the blank. Okay, so the bra is waiting for a ket to come along. Okay, it's waiting for something to come along and fill in the blank. Okay, it's waiting for a function to go here. It's like a subroutine that's ready to have some input. Okay, and then it will run on the input. Okay? So it's ready to receive something in the input place, and then you do the integral. Okay, so first, receive the input, then do the integral. Okay, you do not do the integral before you get the input. Okay, so even though, you could do this integral of just with f and nothing in the blank, don't do it. Okay, you might be tempted to, but don't do it. You have to wait until there's something that goes in the input place before you do the integral. Okay, so this then becomes an interesting situation, okay, where we have now a theory with three types of mathematical objects. Okay, so number one is, let's say we have cats. Number two is we have bras. And number three is we have operators. So let me show you how we would combine any set of these objects in any sequence. Okay, so we'll say, how to combine. Okay, so first of all, if we have a bra acting on a cat. Okay, so that is like what I had on the last page. Okay, so FG combined like that. Okay, and when we're combined like that, then we only have one vertical line. It's just the way people write things. Okay, so this is a bra acting on a cat. Okay, and so what that means is we have our integral dx of f star of x. Okay, here's the bra, And now we fill in the blank, g of x, okay? And now we do the integral. And the result of doing this integral is some complex number. Well, or maybe it's a real number, right? But real or complex. The word complex includes real, okay? It is a complex number, okay? So a bra acting on a ket produces a complex number. Okay, so the ket fills in the blank in the bra, and then you can do the integral and you get the complex number. Okay. This is the inner product. Okay, what about an operator acting on a ket? Okay, so that would be something like Q acting on a ket G. Okay. Well, we know what operators do to functions, right? Operators on functions produce other functions, like that, okay? So if we write this in the ket notation, that would be that Q acting on the ket G produces the ket H. Okay. So an operator acting on a ket produces another ket. Okay. So bras and operators, they each can act on kets, right? But they produce different things, right? A bra acting on a ket produces a number. An operator acting on a ket produces another ket. Now, what about, funny thing, okay, what about if we put the bra and the ket together in the opposite order? A ket bra. Okay, so we could have something like GF. Okay, that's a funny looking thing. What is it? Well, the word for this is an outer product. By contrast with the inner product, that's the bracket. Okay, this thing is called an outer product. And if we want to know what sort of object this is, we could let it act on a test ket. So our test ket, let's call it H, for example. Okay, so if we let the object GF, this outer product, and we let it act on a test ket H, look what we have here. Now this is G times FH, which is an inner product, which is some complex scalar. Okay. This thing is just a number. Okay, so this is a number times a ket over here. Okay, so this combination is a ket. Okay. Yeah, so this is a ket times a number, right? And a ket times a number is another ket. Okay? We could also write it as FHG like that, because it doesn't matter whether we put the number at the front or at the back. Okay. Usually people would write it this way because somehow that just looks nicer, but it could be written this way. So that tells us that the outer product acting on a ket produces another ket. Okay? That's the same thing that I just wrote up here, that an operator acting on a ket produces another ket. Okay? Therefore, the outer product is an operator. The outer product, GF, is an operator. Okay. What about another example? Okay. So what about if we have a bra operator? Okay. So for example, if we have F, Q, like that. Okay. So we can analyze that in the same way. So we will let it act on a test ket H. And what it produces is F, Q, H. Okay. And what is this, right? Well, we already know that the QH is a ket. The F is a bra. So this whole thing is an inner product, which is a complex scalar. Okay, and so the bra operator acting on a ket produces a complex scalar. Okay, that's the same thing that a bra does, right? A bra acting on a ket produces a complex scalar. Okay, so therefore, a bra operator is a bra. Okay, so now the interesting point, really Dirac's motivation for doing all this stuff is that we can set up quantum mechanics working in terms of these three types of objects, right? Kets, bras, and operators. Okay? And it makes an alternative notation for quantum mechanics. Okay, so to see that, let's work in a basis for the wave functions. So we'll work in a basis for wave functions. Okay, so we could say, for example, the energy eigenstates of a simple harmonic oscillator. So when we were studying the simple harmonic oscillator, we worked out that there's a whole set of energy eigenstates, right? That is the special solutions that we were talking about, the solutions of the time-independent Schrodinger equation, okay? And so those are energy eigenstates, which we could call F1 of X, F2 of X, F3 of X, dot, dot, dot. Okay. A set like that. Okay. Or, I mean, this could be for a simple harmonic oscillator. You know, maybe I'll say for a particle in a box. Maybe it's a little bit easier. I'll say for the particle in a box. Okay, so we have this set of functions. Okay? In terms of cats, we could call the corresponding states, corresponding cats, as cat 1, cat 2, cat 3, like this, okay? So this is a nice compact notion where the ket n is a short way of writing Fn of x. Okay? This is a compact notation. This is Dirac notation. Okay, so we know that any arbitrary state, like psi of x, can be written as a sum, n equals 1 to infinity, of some Cn, Fn of x, right? This is what we were doing when we were figuring out the initial condition for a particle in a box. Okay, so in Dirac notation, that is, in terms of cats, we would write this as the state psi, the ket psi, is the sum from n equals 1 to infinity of Cn times the ket n, like that. Okay, so this is our, nice compact way of writing this equation about functions, right? So this is an equation that says one function is a sum of coefficients times other functions. And this says the same thing in terms of kets, right? That the ket psi is the sum of coefficients times the ket n. Now, this is a basis for the kets. What about the bras? Okay, well, there is a related basis, a dual basis for the bras. That is, we could write a set of bra 1, bra 2, bra 3, etc., where bra n means an integral dx of fn of x star times fill in the blank. Okay, so this is a bra which is ready to receive its input that goes right here. Okay, and then you multiply it by one of the functions in the particle in the box set of special functions, and then integrate. Okay, and then any bra can be expanded in this basis. That is, if you have any bra that comes along, like psi, we could write it as a sum of n equals 1 to infinity of this bra n times the coefficient Cn complex conjugate. That coefficient is a number, so it could go either before or after the bra. Could go before like that. Okay, so any ket is a sum of the basis kets. Any bra is a sum of the basis bras, like that. So now all of our stuff with bases, we can write in this compact notation. Okay. So, for example, we talked about orthonormal bases. So we said for functions, if we have that the integral of fm star of x times fn of x, this is equal to the Kronecker delta symbol, delta mn. Okay, what that means in terms of bras and kets is that the bra m acting on the ket n is delta mn. Okay. Now we could use this to figure out the coefficients. So if we want to figure out the coefficients, this is like what we did with the Fourier trick, right? To find the coefficients in a Fourier series. Okay. So if we have that psi is some sum of Cn times the ket n, okay? And we want to know what are these coefficients, okay? So to do that, we could let the bra m act on both sides. Okay, so on the left side, we have m acting on psi over there. That's an inner product. On the right side, we have m acting on this sum of Cn n, and then the sum just factors out. And the Cn coefficients just factor out. And then we have the inner product of m with n. Right? So that's the bra m acting on the ket n. And that's what's right up there. Okay, so this is delta mn. And so, now we have the same story that we've talked about a few times in the semester, right? Where there's a sum of an infinite number of terms, but only one term in the sum is not zero, right? Everything else is zero. The only term that's not zero is when m equals n. And then this Kronecker delta is 1. And so in that term, this is Cm. Okay? So Cm is the inner product of state M with psi. Okay, and likewise, if we want to work with a sum of bras, the same thing works, okay? And so if I say the bra psi is the sum of n equals 1 to infinity of the bra n times Cn conjugate, then we could say let both sides act on m, and then what? Well, then we would have psi m on the left side, and on the right side, sum of n equals 1 to infinity of n Cn star m, like that. And the Cn's are coefficients, they're just numbers, so they can factor out. So Cn star nm, and this thing is the Kronecker delta nm. So we get that this is Cm star. So Cm star is this inner product of psi with the basis ket m. And this equation is perfectly consistent with this equation down there, because when you reverse the order of things in an inner product, you take the complex conjugate. Right? So doing it in this order gives Cm, doing it in this order gives Cm complex conjugate. Okay, so this is the Dirac notation version of what we did with writing a wave function as the sum of the special solutions. Right? And so, the notation takes a little bit of getting used to, but it's a nice compact way of doing it, right? Without writing out everything explicitly as a function of x, and without writing everything as an integer, excuse me, integral. Okay, now what else can we say in terms of this notation? Okay. Another concept in this notation is, I'll just mention briefly, a projection operator. Okay. Geometrically speaking, right, sometimes, here I'll do a little geometry interlude over here, right? If we have our unit vectors in terms of x and y, like that, okay? And then we have any old test vector, v, like this, okay? Sometimes we talk about projecting v onto the x-axis or the y-axis, right? We can say, let's project it down like this, okay? And we get a vector here. This is v projected onto x. And over here, we could project it there onto the y-axis. So this is v projected onto y. Okay. And maybe we would want to have a nice way to express what is that projection in doing geometry. Okay, so for v projected onto x, we could say, well, let's take, what's the magnitude of v projected onto x, right? That magnitude is x hat dot v, like this, okay? But if we want a vector with that magnitude in the x direction, that would be x hat times x hat projected times x hat dot v. Okay, so this is a vector, right? This here we have a dot product, that's a scalar times a vector, so it's a vector. Right? So this is a vector which represents this vector, right? The v projected onto x. Likewise, over here, this vector, like that, that is y hat times y hat dot v. Okay. So this is taking any old vector v, and you get the dot product with y, that's a scalar, times y hat, that's a vector again, that's this vector. Okay, so this is a projection, right? This is what we mean geometrically by a projection of a vector onto some axis. Okay, we might want to do the same thing with Hilbert space, okay? And so we might want to think of what is the state psi, the ket psi, projected onto some basis ket n. Okay? So that would be, we take the inner product of n with psi, and we have that amount in the n direction. Okay? So this is an object sort of analogous to this or this, okay, in the infinite dimensional Hilbert space. Okay? This is something proportional to the ket n because it is the ket n times a complex scalar over there. Okay? So it's in the direction of the ket n, and it has the right magnitude, right, to correspond to psi. Right? So we would say that the outer product n is a projection operator. That this outer product takes any ket that comes along and produces the projection of that ket onto n. Okay. The same way that, here we have a projection of V onto X, so here we have a projection of V onto Y. One more aspect of that is something you can see in geometry. Okay. In geometry, we know that V, the original V, is the vector sum of the X projection plus the Y projection, right? If you do the X projection plus the Y projection, you get the original vector. Or if it were in 3 dimensions, you need to do the X projection plus the Y projection plus the Z projection. Okay, but it brings you back to the original vector. Okay, so in vector notation, we could write that as V equals X dot V plus Y dot V, right? That the sum of all the projections gives you back to the original vector. Okay? It's like that in Hilbert space also. So in Hilbert space, we could say, what is the sum of all the ends of the projection operator in the n direction? Okay, and this is going to be just the identity operator. That is, it gives us back the original ket, whatever we started with, the same way that we get back to the original V over there. So the identity operator, it's something that we might write as I hat, like that, an identity, or we could write it as 1 hat. That is, it's the operator that operates on a function by multiplying that function times 1. Right? So it does nothing to the function. right? Multiply by 1 does nothing. Okay? So this is, a particular kind of operator. It's sort of a trivial operator that does nothing, right? But sometimes that's useful in calculations. Okay, and so I will use that in the calculations coming up. Okay, how am I doing on time? Actually, I'm almost out of time. I'm almost out of time. I think I'm going to stop here. I'm going to stop here because I'm about to start something bigger. Okay, so then, so the next thing is, use this approach for operators. So I'll say use this approach as another way to understand what an operator does. Okay, so that is going to be the beginning of the class. No, it's going to be the entire class on Thursday. Okay, so I will talk about that on Thursday, unless, of course, you have other last minute review questions just before the test happens. That sounds like a threat, doesn't it? Ask me some questions or I'll teach you a new thing. That'll teach you. All right. That sounds like a threat. Well, so be it. Okay. So I will, I guess, stop here for today and I'll begin talking about operators in Dirac notation on Thursday. All right. Good. So long, you guys. I will see you on Thursday.